Hey, P Calculus, I've got a new video for you. We'll call this 4.6. It's the second related rates video. I'm just going to do number 20 and number 30 from the problem set that I posted on Google Classroom. The one that I started in class, but then we kind of ran out of time before we got through the whole thing. So, number 20, right here. It says an aircraft is flying horizontally at a constant height of 4,000 feet above a fixed observation point. There's a figure below this, but I'm not going to scroll down to it. At a certain instant, the angle of elevation theta is 30 degrees and decreasing, and the speed of the aircraft is 300 miles per hour. They're asking us to figure out what the speed of theta is decreasing at that instant, and then expressing the result in degrees per second. So the first thing we should probably do is get a good picture for it. So it's not this picture of the guy doing whatever he's doing down here with the lamp. We've got an airplane, we'll just call it this point off in the distance because we really can't see it. It's 4,000 feet above the horizon. Or I guess above sea level, we'll say. And the observation point's down here. Now, if you're observing, there's going to be a line of sight to the airplane. So here's the line of sight. All right, so the plane is constantly 4,000 feet above that fixed observation point. So this vertical distance is always 4,000 feet. It's the horizontal distance that's always changing. And I guess we could say that this distance is also changing as well, so maybe give that a variable if we need to use it. So I'll just call it C for my a squared plus b squared plus c squared hypotenuse. All right, now, they're talking theta here. So how fast is theta decreasing? That's going to be a d theta dt question. So we know this is theta. We want to use the 300 miles per hour. The speed of the airplane is 300 miles per hour, which means dx dt is 300 miles per hour. So just mapping a few things out. 1, dx dt equals 300 miles for every 1 hour. Now, noticing right away, they want our final result in degrees per second, and we have 300 miles per hour. Perhaps it's a good idea to just change that to feet per second so that we can get the same measurements for our 4,000 feet, our 300 miles, and our 1 hour. Let's just turn this into feet per second. So to do that, I'm going to do some dimensional analysis, which is just a fancy way of saying I want to get rid of the hour units and replace it with seconds. So I'm going to say the rate for hours to seconds is there's 1 hour, and I'm going to put it on the top of the fraction to get rid of the hours, for every 3,600 seconds. So if I do that, I now have it in terms of miles per seconds because the hours units cancel out. I want feet per second. So I'm going to multiply that by, we need to put the miles on the bottom. So it's for 1 mile, we've got 5,280 feet. So now my miles units, they cancel. And now we've got our speed in terms of feet per second, which is going to make the calculations accurate. So 300 times 5,280 divided by 3,600 comes out to be a nice, neat 440 feet per second. So dx dt is 440 feet per second. That's good to know. So now we need to turn x, well, first of all, we need to create a primary equation. So let's do that. Do we have enough room over here? Probably not. Let's just go off to our surplus location. So what's our primary equation? And I'll try to find a darker marker so you guys can see it better. Primary equation. So we need something with the theta and the x because we have a dx dt and we're looking for d theta dt. So in class we talked about how tangent of theta is equal to the opposite side over the adjacent side. And that pretty much does it for us. Now there's a couple different ways in which to visualize this equation. I don't know what works best for you guys, but I was thinking about it and I thought, what if I multiply the x to the other side? So times x. Now we've got 4,000. And what if I took the tangent of theta and moved it to the other side? So if I divide by tan theta, and divide by tan theta over here, dividing by the tangent is the same thing as multiplying by its reciprocal. So what's the reciprocal of tangent? Cotangent. So I don't know if you guys are comfy with this, but I just thought to myself, I got rid of the fractions. Maybe this is a better primary equation to take the derivative of. So we've got our primary equation. We don't have to do any quotient rule or product rule or even deal with a fraction at all. If we do d dt of both sides, you get dx dt on the left with nothing else. On the right, you get 4,000. The derivative of cotangent is negative cosecant squared. So I'm thinking to myself, like, that's not a bad deal to have negative cosecant squared versus, I think we would have gotten secant squared on the other side. Now keep in mind, you got to now do the chain rule of the inside. You got to take the derivative of theta, which is d theta dt. All right, now we can start plugging stuff in. I'm going to keep the units too so we can keep track of things. So I got 440 feet over seconds over 1 second is equal to negative. Now, technically, this was 4,000 feet divided by x feet. I think I'm going to deal with the units at the end because I'm already confusing myself. (440) equals negative 4,000. Now, it says at the instant that theta is 30 degrees. So I'm looking for the cosecant of 30 degrees, and I'm squaring that number times d theta dt. Now, when you think about a 30-degree angle here, I could use the sine of 30 degrees equals 4,000 over c, right? That's what sine is, and cosecant is just the flip of sine. So sine of 30 degrees equals 1/2. If I flip that, I get cosecant of 30 degrees, which is 2 over 1. So I'm squaring 2 over 1. I'm squaring 2. That's going to be 440 equals negative 4,000 times 2 squared d theta dt. And then really all you got to do here is take 4 times negative 4,000, which is negative 16,000. And then I could reduce this fraction. I got a calculator. Maybe that'll quicken the pace. It basically gives me negative 11 over 400. Which if we interpret that, that should come out to be 11 degrees every 400 seconds. And that's what that shapes out to be. Okay. Let's check out number 30. Can you guys see that whole thing? All right. So it says an aircraft is flying at a constant altitude with a constant speed of 600 miles per hour. It's this right here. An anti-aircraft missile, oh no, is fired upon a straight line perpendicular to the flight. So here we go. Here's the anti-aircraft missile. Here's the aircraft at a point P. At the instant the aircraft is 2 miles from the impact point, the missile's 4 miles from the impact point, and flying at 1,200 miles per hour. At that instant, how rapidly is the distance between the missile and aircraft decreasing? All right, so this one, we clearly have a right triangle situation happening. All right, if you look at it from this perspective, here's my airplane, and here's the missile. Now, as the two are getting closer and closer together, this distance right here is technically the distance between the airplane and the missile. So, as the airplane gets closer to the point D, I guess like we could call it X, dx dt gets smaller, dy dt gets smaller, and dz dt also gets smaller. So we've got 3 different variables, 3 different rates of change. A lot's going on here, but you got that, okay? And I think we've got more information from this problem than what we've had in previous problems. So when you see that you've got a triangle and we're not really messing with the thetas, we're not messing with the angles inside here, we can just be pretty confident that it's going to be Pythagorean theorem for our primary equation. And that comes out to be the case for number 30. So we're going to go, instead of a squared plus b squared equals c squared, x squared plus y squared equals z squared. All right? None of these are fixed except the point. All right? So x is changing, y is changing, and z is changing. So when we take dt of everything, you're going to get 2x dx dt plus 2y dy dt equals 2z dz dt. Now you can divide out the 2. Just to clean things up. And this is the point at which we dig in. The aircraft is flying at a constant altitude with a constant of 600 miles per hour. So the dx dt is going to be negative 600 because it's decreasing the distance x from the fixed point. So I can put negative 600 for the x. Oh, no, for the dx dt. My apologies. dx dt is negative 600. How far is the airplane from the point of impact? It's 2 miles. So x now is 2. Moving on to y. The missile, sorry, do I pronounce it missile or missile? Missile. I don't know. I haven't decided yet. So the missile is going 1,200 miles per hour. And again, it's decreasing the distance y. So I'm going to make it negative 1,200. The y value is it's 4 miles from the point of impact. So I'm going to put 4 in for y. And then z, so this is 2, this is 4. Z, we don't know what dz dt is, but we can certainly figure out what z is because 2 squared plus 4 squared is equal to z squared. So this is going to be 4 plus 16, which is 20, equals z squared. We've got z. It's root 20. And then dz dt is the last part. We're looking for dz dt. So yeah, all we got to do is divide everything by root 20, and we've got our dz dt. So, the wonders of technology, I can just use the calculator. I believe it's going to be, well, you know what? Let's just do it. Plus, so it's going to be negative 6,000 on top divided by root 20. If you just want a decimal approximation, it's negative 1,341.64. And at every point in here, it was miles per hour or miles, so there was no confusion with the units at all. All right, guys, hopefully that was helpful. Thanks for watching.